This is basically about the morphology of soot and a model of how soot structural variations occur in typical combustion emissions. And I'm going to start with an overview of the supporting evidence for this, and then just finish with a few new things on where this might lead. This, in a way, might be an alternative view of some of the things that Alla was talking about a few talks ago, and I hope it's not contradictory, but maybe it's a different view of some of those things. So first of all, this all started with looking at TEM images of this sort. This is very typical. We'd see a large soot aggregate with relatively large primary particles and small aggregates with small primary particles. And it doesn't look like this larger aggregate is made up of the same things that built this smaller aggregate. And this is not just one example. Raman Dastanpour, for his thesis in this paper in 2014, looked at GDI soot, natural gas engine soot, laboratory burner soot, and jet engine soot. And each of the dots on the right here is from a TEM image of a single aggregate. It's the average primary particle size in that aggregate plotted against the aggregate size represented by the projected area equivalent diameter. And there's certainly a lot of scatter here, and this is because there are variations in primary particle size even for a given soot aggregate size, but there is a robust correlation here with larger aggregates tending to give you larger primary particle sizes. And we've looked at thousands of images by now, and this is our impression of what causes this. If you could imagine a typical non-premixed flame where soot is forming in small local regions, the vast majority of the soot is oxidized before it's admitted to the environment, so the concentrations are greatly diluted before you would end up collecting and sampling the soot. And so imagine we could color code these aggregates formed in different regions. You might have some aggregates with small primaries, others with larger primaries, and you've got these variations in primary particle size that originate from the local regions they were forming in. Of course, when we put this on a TEM micrograph, we can't distinguish these particles, but suppose we could, maybe Alla could do something like this. You would get the aggregates lining up on your plot of primary particle size and aggregate size in this way. And if we put a fit through this on a log-log scale, we'd get this correlation through this cloud of points. And the slope of that line in the log-log plot would be what we call the DTM, or the exponent relating primary particle size and aggregate size. So I've said we've seen this in lots of different images, and there's another thread of evidence, and this work has come through mostly collaborating with Jason Olfert. If you have a CPMA and an SMPS, you can measure the effective density. And so you can go from the irregular soot particle, get these effective diameters and the effective density. And then from that, you find the mass varies with the mobility diameter to some scaling exponent where dm is the mass mobility exponent. And by the way, this schematic, going back here this cartoon of a soot aggregate here is an example of what we'd say is a not externally mixed soot particle. Here we have large and small primary particles all within the soot aggregate. And so I say that's very atypical, whereas the logo from the Cambridge Particle Meeting, I'm pleased to say, sort of follows what we see from the external mixing hypothesis, where the size variations of primary particle size are externally mixed in the aerosol. So back to the effective density, if you take the data from many different studies, the effective density falls with mobility diameter, and that typical fall is related to the mass mobility exponent. This is all stripped soot, so no coatings on this. And putting a line through all of that, we get this characteristic curve with a mass mobility exponent of about 2.48, which corresponds to, and I'll explain in a minute, corresponds to a certain characteristic increase in primary particle size with aggregate size. The results are color coded here. So compression ignition engines, the black circles tend to be above this line on average. And burner soot, non-premixed burner soot pretty much follows this line, and GDI engine soot seems to be below typically. And each one of these colors corresponds to many different publications. Okay, so we can actually see whether this effective density data is consistent with the TEM data, but I'd like to explain how the external mixing hypothesis relates to the effective density measurements, or at least interprets what I think we're seeing here. So again, we've got the non-premixed flame soot from different regions with different primary particle sizes, all being collected by your instrument. If we looked at a diffusion limited cluster aggregation fractal aggregate, we would expect the effective density to fall according to a mass mobility exponent of 2.2. So if we were able to sample soot from only one homogeneous region of the flame, like the green there, we should see it falling along that curve. And if we looked at the red soot from a different region, we should also see the same drop in effective density. But we don't get to collect soot only from those local regions. It's all mixed in our sample. And so when we collect this data and take the peaks of the distributions that we get from, say, our SMPS measurements, we put a fit through that, and we get a higher effective density, higher effective density and a higher mass mobility exponent. And so this is an interpretation of why we get this effective density that doesn't fall as fast as you'd expect for fractal aggregates. We're interpreting this as the fact that we've got this collection of aggregates with different primary particle sizes. We can use what's known about the mobility of fractal aggregates and relate the primary particle size that we expect for the aggregate to the effective density measurements. And then down at the bottom, we can relate the exponent that we should see from the TEM measurements to the exponent that we get from the mass mobility measurements. And what this tells us that if we have a mass mobility exponent of about 2.5, we would get a scaling in the transmission electron microscopy images of about 0.38. This relation also tells us that if our mass mobility exponent is 2.2, we don't expect to see any change in primary particle size with aggregate size. And this part at least is consistent with what Alla was showing a few talks ago. So if we take the TEM data, and then that's what each of the dots is here. It's an individual aggregate for a particular model flare fuel. And we look at the primary particle diameter against aggregate size. We see this upward trend. The solid line is just the fit, a linear relation in log space. And then the dashed line is from independent SMPS CPMA measurements of the same sample, the same source, and then using that model for the drag. And we get a fantastic agreement between the effective density measurements and the TEM measurements. Now, I won't claim that every time we do this, we get exactly this close an arrangement, but it is pretty consistent. And on average, the model is quite accurate. So this is an indication that we have, I think, a reasonable interpretation of what's happening with soot structural variations. And I just want to give you three areas where we're trying to push this a bit further. The first is in using two-dimensional mass mobility distributions. And this is work mostly led by Tim Sipkins, working with Jason Olfert as well as with my group. And here's an example of what Tim has produced for some data from a flare in a laboratory at Carleton University. It takes a little while to get used to these plots. The vertical axis is mass, so you can measure that with your CPMA and a CPC, and then the horizontal axis is your mobility diameter. And the marginal distributions here, here's the marginal mobility distribution. It is what you would get if you had only the SMPS, and the marginal mass distribution is what you would only get if you had only the CPMA and a particle counter. But if you do this in a tandem arrangement, you can get the joint distribution, which is approximately joint log normal. And so you can see that you get this elongated ellipse. As the mobility diameter goes up, so does the mass. And the slope of that is 2.55, which is fairly close to the result that we'd obtained by surveying the literature for mass mobility exponent. The other thing that you can get from this that you can't get with the traditional effective density measurements is that here we actually get the width of the distribution in mass mobility space. And so we believe from the TEM measurements and from other sources that we should expect a broad distribution of masses for a given mobility diameter. And this is something that you could get with the two-dimensional presentation. We are interpreting this primarily as differences in primary particle size, but could also be, well, and inevitably would be partly due to differences in morphology and how compact the aggregates are. So those effects are lumped together. So another direction that we're looking at with this model is the impact on optical properties. And so this is just a modeling study where we've taken T-matrix calculations for fractal soot aggregates published previously. And we're not changing the structural model for each aggregate. What we're doing is we're saying we have populations of aggregates with different primary particle sizes, and that primary particle size is varying with mobility size. And so this plot shows the MAC number, which you would care about if you're measuring soot absorption at a particular refractive index and a particular wavelength. Again, we're not looking at changes in refractive index here. We're only looking at changes in the structural model. And the solid line corresponds to a conventional model where the primary particle size does not change with aggregate size. And that again corresponds to a mass mobility exponent of about 2.2. And the T-matrix calculations show that the MAC changes with aggregate size due to interactions of the primary particles. If we look at our primary particle sizes increasing with mobility size in what we think is a typical way, we end up with the larger aggregates having larger primary particles, and that gives you an increase in the MAC number for the larger aggregates. And if we have maybe an extreme model with a steeper dependence of primary particle size on aggregate size, we get an even steeper increase in MAC up to this value, and then a decrease. So these are differences that should be measurable, and it would be interesting to see if we can pick them out in data later. And the last thing that I'm going to talk about is the fact that this external mixing hypothesis actually must break down, and we certainly see evidence of this in some images where you would look at a particular aggregate and you see it's comprised of a clump of large primary particles here, about 34 nanometers on average, connected to a clump with much smaller primaries, and then a third grouping here. And this, I suspect, would be an indication of the post-flame dilution processes. And it might be interesting to see if it would be characteristic of different kinds of sampling systems and different kinds of engines. Should be related to coagulation post-flame. The challenge in looking at this experimentally is that the image processing is quite hard to do, and getting large enough samples is difficult. But I think this is probably on the horizon. So in conclusion, we see the primary particle size variations as being mainly externally mixed between aggregates. We see relatively uniform primary particle sizes in typical aggregates. This results in quite broad two-dimensional mass mobility size distributions. We're just learning how to visualize this and measure it, and it may be something that's going to be characteristic of different combustion sources, although this is a new way of looking at things. Another thing we're starting to look at is the fact that the distribution of primary particles within aggregates in a polydisperse aerosol is going to affect the optical properties. And finally, this model of soot structure, I think, describes normal soot, but it clearly breaks down, and that would be an interesting thing to look at in the future. So with that, I think there's probably some time for questions.
There's technically all the rest of the day, but there are two questions already, in fact. So we have Jose Moran. I will unmute you. Please say your question when you're unmuted.
Okay, thank you, Dr. Rogak, for the very nice presentation. I really enjoyed it. And I wanted to ask you about your definition of the primary particle diameter, because, for example, when we consider the aggregate to be, for example, we consider the primary particle to be in one-point contact, we always say, okay, the diameter of the sphere. But when they are in overlapping, it starts the question, some people propose, for example, to work with the ratio of volume and surface of the particle. So what is your definition of the primary particle from this point of view?
That's an excellent question, and I'm very sorry I had to let the dog into the room. It was banging on the door. So, we've been using mostly manual image processing as our baseline here, and this is certainly a subjective thing. I think we've gotten some consistency over the years with multiple users of the TM, but certainly as you start to get very overlapping primaries, it's much harder to say. And I guess directly your question is, if we have overlapping primaries, it would be what a human sees as the circles that describe those primaries, even if they're overlapping. Yes. But when you start to compare that to mobility methods and surface area methods, that is indeed a difficult question. I hope I answered your question.
That's okay. Thank you.
Okay, thank you. Next we have Georgios Kalasidis, if I will unmute you.
Yes, thank you very much, Stephen, for the excellent presentation. I really enjoyed it, and I have a question regarding the external mixing that you are proposing. So at the moment, you have talked mostly about mixing of soot agglomerates that have different primary particles. I'm wondering if they are coming from different parts of the flame or of the combustion chamber. They might have also different composition. So have you considered this? Do you think this is possible? And most importantly, if you have such data available to support this.
That's a great question. I think Alla probably has better instruments to look at this. What we have done is we've done samples that are segregated by size, by mobility size, and because there's this general trend of primary particle size changing with aggregate size, when we do mobility segregated sizes or aerodynamic size segregation, we also get a primary particle size segregation. And we do see differences in things like the Raman spectra that we get. And then there was some work that we did with the NRC people a few years ago where the MAC number changed when we looked at mass selected sizes and looked at the optical properties. So I think there's an indication that there is differences in the physical properties, but other people have better instruments to do that experiment.
Okay, well, coincidentally, Alla has a question, so maybe Alla can comment as well. So I will unmute you, Alla.
Thank you. Very nice talk, and there are no contradictions. It's all in perfect agreement. When there is not just one type of fractal particles made out of one, on average, primary spherules, you have one slope. As you keep adding either different spherules, like your external mixture, or more compact, different particles, your slopes start going up. So there is no contradiction. We do have a lot of data for spark ignition direct injection engine, where we simultaneously were producing two fractal soot particles, one made out of little spherules and another one from large spherules. It was very puzzling because we looked, is it effect of density composition, and we were getting two parallel effective density versus mobility lines, like identical composition. So all it was suggesting that it's different in primary spherules, they are composed. It's like you picturing these different external mixtures. So first we were surprised, saying, how come little guys agglomerated with little guys and big ones with big ones, and they co-emitted under the same conditions. But then by changing the timing between fuel injection and spark ignition, we related it to heterogeneity within combustion engine, to more rich and more mixed zones. So as you sweep in this timing of injection, you could see how you could move from one mode to second mode, and there is possibility to relate size of this primary spherule to this mixing within chamber. We then later on did experiment with pre-mixed, pre-evaporated fuels, which supposed to eliminate the whole coexistence of these two populations, and it went away. We just had one size present. So if somebody, like Georgios was asking, do you have data, is interested and to work with data, I would be happy to share. But it's very nice stuff. Thank you.
Thank you.
Thank you. Okay, last question is from Reza. I'll unmute you. I'll try to.
Can you hear me?
Can now, yeah.
Okay, thank you, Sid, for the presentation. My question is, if you look at the primary particle size distribution for mobility selected particles, do you see a correlation between, for example, overall equivalence ratio or the engine load, or something that is in that line? Because when I look at some data for jet engines, it looks that with increasing load, the primary particle size distribution within agglomerate, size selected agglomerates, increases. And I'm wondering if you also see such trends.
So we have not done mobility selected primary particle sizing, but I will bring back this plot that Tim Sipkins produced. And this is in a paper just accepted by Fuel. So I'm suggesting that the slope of this ellipse and the width of it, it tells you something about the primary particle size distribution. And so for a given mobility diameter, if you cut across here, where you cut across in mass is going to be indicative of the primary particle size distribution, assuming it's the same fractal dimension. Now, what we see for a whole family of different fuels, I forget how many, 10 or 12 different fuels, you get almost the same ellipse. This is the same burner, but changing the fuel dramatically and getting orders of magnitude difference in soot emissions. And what happens is that you're following the same trajectory, but the bright spot on your ellipse is shifting along this line. So all of the different fuels kind of live in a family of ellipses that translate up and down this line. So there are definitely differences in distribution, but they kind of live within this narrow envelope in mass mobility space. I think that's the best way I can answer that question. I don't think I've directly answered it though.
Okay, thank you very much. Thanks very much, Steve. Excellent presentation. So that is the end of the program. So I'd like to thank all of you for coming, and I'd particularly like to thank Molly for organising this. She's done a fantastic job. I'm sorry we can't go down the pub now. Well, you may be able to wherever you are, but I certainly can't where I am yet. So yeah, I hope to see you all in person. I'll hand back to Adam for anything he wants to say. Thanks, Adam.
Yeah, thank you, Johnny, for covering that. I have nothing further to say other than, yeah, I think you all deserve a beer, and perhaps Jason's presentation indicates that's where we should leave it, at least at this point. I appreciate the responses to the in-person poll. It looks like there's maybe some support for future years having an online component while retaining an in-person component where people could socialize a bit. So we'll certainly take that on board for future years. So thank you all for contributing. This has been fun. We to be honest, we were on the fence about whether to hold it online and whether we had the capabilities and the technical prowess to be able to pull it off, but I think it went fairly well. So I appreciate everyone kind of sticking with us to the end. And again, all of this will be available via kind of a website. We'll talk to Combustion about maybe posting this on the CPM website, the recorded video to all of this. So that's all I have. Thanks everyone once again. It's really been a joy.